part where A is an instance of show, and that's what the backtick curly braces is saying. So A is a type such that you can find a show instance for it. And now we take a value of A and we return a string, and we use the show operation from the show type class to convert our little a to a string in a generic way. And now we can apply show1 to things like true and 42 and get back strings in both cases. And the thing that's interesting, obviously, is that the two curly brace delimited parameters to show1 are both being filled in implicitly. Not just the type, but also the show instance. Okay, we can write functions that have multiple type class constraints. So here is a function show2 that takes types A and B, both of which are instances of show. And now we can apply show2 to pairs of colors or pairs of different things. As long as those different things both have show instances, everything will work. Okay, here's a different type class. This is a quite useful one. It's called EQ, and it classifies things that can be compared for equality to return a Boolean. And here are the Boolean and natural number instances. Okay, so we can define kind of basic type class instances for all the primitive atomic types that we want. What about structured types? Here's a type class instance for show of pairs, which says, you can think of this as a function between type class instances. That's actually what it is. It says, given types A and B, and given evidence that A and B are showable, then the type A cross B is also showable. And here is the show instance for that type. So it looks just like an instance declaration that we've seen, except that it has more parameters. It takes not just types, but also some evidence involving those types as parameters. And now it's using show A and show B to construct the show instance for A cross B. Similarly, here is an EQ instance for pairs, using the EQ instances for the components of those pairs. And again, similarly, here is a show instance for lists, and it uses an auxiliary function just to do the string munging of putting the commas in the middle. Okay, so given all of this, we can now write things like show for a complicated type involving lists and pairs and so on, just by using show at an appropriate type and relying on the type class inference mechanism to fill in all of the boilerplate. Okay, so that's nice. So a minute ago we saw how to derive type class instances from other type class instances. We can also derive type classes from other type classes, and that is the notion of subclassing. So, for example, suppose we want to compare things not only for equality, but sometimes for inequality. So we would like to have a less than or equal operation, but less than or equal in this view of the world only makes sense for things where we can also compare them for equality. So we would like to have a type class of including the less than or equal operation and the equal operation, but we don't want to write all of that again, all of the hideous complexity of the EQ type class and its instances again. So we're just going to write the new part. So the new part is just the LE operation, and then we put at the top a constraint on the class definition that says whenever we're going to define an instance of this class ORD, we must supply evidence that the type that we're putting into the ORD class is already an instance of the EQ class. And for example, we can build an instance of NAT ORD because we already have an instance of NAT EQ. Okay, now when we write a function that's going to use the LE, it actually needs to be passed a type and two pieces of evidence. Evidence that it has an equality method and evidence that it has an inequality method. So functions like max are actually going to take multiple evidence parameters, kind of walking all the way up the subclass hierarchy.
So Coq won't automatically supply the...
Well, couldn't you automatically fill them in? Yes, of course you can. We'll get to that in a minute. Or maybe it's just in the text. But yes, they can be inferred automatically. So I'm showing you what's there. But in fact, if you leave some of that out, Coq will fill it back in. I think there's an exercise inviting you to experiment with that in the text. Okay, so how does all this happen? Let's look under the hood. So this, the key to it is this backtick notation. And actually, this is one of two key elements. And this backtick stuff is actually a fairly simple thing. So this is the simpler of the key elements. It does so-called implicit generalization. And the way it works is, if you put something with a backtick in front that mentions, so you put a binding with a backtick in front that mentions a variable that is currently not bound, Coq will automatically bind it for you. And in order to prevent mass confusion, if you just make typos or things like that, and you wouldn't want your mistakes to automatically get generalized, so the type class mechanism requests that you first declare these are the variables that by convention I'm going to want to be implicitly generalized. So let's choose A for purposes of this discussion. And now, when we write this backtick show A, Coq says, oh, I haven't seen A. There's no A bound in the context. So I'd better put a universal quantifier for A at the front of the type of this thing. And we can see that if we print it out, that here is the lambda A, the fun A, and here is the show evidence. This is what we actually wrote the abstraction for. This one was filled in automatically. Now we can go further with hiding things. So in the thing that we printed out, you saw that, this evidence actually has a name. We can give the evidence a name explicitly if we want. Usually the convention is not to because it doesn't get used here explicitly. Of course, implicitly it does get used because H is where the show operation for A's is coming from. But all of that boilerplate is under the hood. So usually we don't write this. Some people will write an underscore there just to remind themselves that there is something being bound. I prefer not even to write the underscore colon personally, but you can make your own choice. And all these different ways of defining the show1 function are actually the same. Okay, so one thing that's useful about this is that it works recursively. That is, we can leave out, as we noticed a minute ago, the kind of extra evidence arguments. If we ask for evidence that A is an ORD, we'll get both an automatic binding for for the type A, and an automatic binding for the evidence that A is an EQ. Okay, let's lift the hood some more. Records in Coq are actually not built in very deeply. They are pretty lightweight syntactic sugar for products. So here's the convenient syntax for records. We define a record by giving it a name, by giving it a constructor. So this is like Haskell. There's a constructor build point associated with the point record, and you can use it explicitly. So the record declaration actually internally translates into an inductive definition where build point is the single constructor of the inductive type. And if you want, you can explicitly apply the build point constructor to arguments. And that will work just fine. Or you can use a record value notation, in which case you name the arguments px and py rather than just giving the values. And you can give them in either order, and the surface syntax will sort them into the right order for you. That's really about all that's going on with records. Oh, one more thing is that you get field dereferencing with a slightly clunky syntax, because dot is also used for other things like modules in Coq. So you say record value dot parentheses name of field to get the value out. All right. Record declarations can be parameterized, like most things in Coq. So we can have a polymorphic record declaration that takes a type argument and includes a label field that belongs to whatever that type is. And now, type classes are really just records. Plus, it's not absolutely the same to declare something as a class and to declare it as a record. There's a little bit of extra magic where if you declare something as a class, then hints get installed in various search databases, but they're almost the same. So if we define the show type class as we did before, for example, and then print it out, it will print as a record with a build show constructor and a show field of type ArrowString. So internally, type classes are very little more than just records, record types. And then, of course, if a type class is a record type, then a class instance is a record value. And that is also true. And similarly, an overloaded function like show is really just a record projection. So when we say show, we're applying a function that takes an A and some evidence that A belongs to the show type class. This name show0 is automatically generated. And we're extracting the contents of the build show constructor, which is the only way of building things from that inductive type, and applying it. All right, so all of that kind of sets up the structures. Now we need to see how the inference works, and that's the other part of the magic of type classes. So for example, if we write show42 and print it out, what we actually get is show nat and then show nat, the show instance, and then 42. So show has some implicit arguments, that need to be filled in whenever we use it. How does that happen? Basically, in a similar way to the way the NAT argument gets filled in, but using a more sophisticated search mechanism. So rather than just using unification, it's using essentially auto to try to construct evidence for the assertion that NAT is an instance of show. So it's doing that using literally the auto proof search mechanism, using a special hint database called the type class instances hint database. And we can see what's happening if we turn on a switch called set type classes debug. You will be familiar with this switch pretty soon if you use type classes a lot, because this is the main way of seeing what's going on when type classes are not giving you what you want. So if we set type classes debug and then we try to find the type of show42, we see a message that says we're looking for the show instance of NAT, and oh, we found it. So essentially we're looking for something of type show NAT, and oh, show the value, the instance show NAT, is in the hint database immediately, so we just find it. Now, more interestingly, if we look for the show instance for a pair of showable things, we have to search a bit deeper. So we're looking for show of this pair type, and here we're attempting to apply show pair. And that requires, after a little bit of unification, we discover that requires finding a show instance for bool, and here it is, and finding a show instance for NAT, and here it is. Okay. With all of this setup, you might wonder, oh, can I use type classes to fill in not only code, but also proofs? And the answer is of course, and it would not have been interesting to add type classes to Coq if you couldn't. So everything we've done extends to filling in proof arguments, not just code arguments, not just values. And that fact is heavily used in the libraries in Coq and the developments in Coq that use type classes. We don't have time right now to go deeply into this, so for now I'm just going to let you know that, that all of these features are there when you want to use type classes in proofs. And for today, I'm going to continue with looking at just how type classes work, and then later on how they're used in QuickChik. Let's see. But let me give you a taste. So let's have a subclass of EQ called EQDEC. And so besides the EQ method, an EQDEC instance is going to have a method called EQBEQ, which asserts that the equality method returns true exactly when its arguments are equal. And now, in order to build an instance, we have to supply evidence. We have to supply that method. Namely, we have to supply evidence for the truth of that claim in the particular case of, in this case, NAT. Here, it happened that we had already proved that. If you haven't already proved it, you can do this. You can give an instance declaration and leave it out. Leave out the field that you're required to put in. If you do that, Coq will dump you into proof mode and ask you to use tactics to fill in the missing bits.